Welcome to Six Sigma Black Belt, Course 8, Module 3, Robust Designs. When developing a new product, we must be well aware of our functional requirements for the product. These functional requirements are translated from the customer's wants and needs into concepts, systems, and designs to satisfy these necessities. Consider all alternatives in your assessment and ensure that your final choice is functionally robust. This implies that it can still function adequately under desired performance capabilities while in the presence of chance-caused variation or noise. Parameter designs are meant to boost functional robustness of the process such that desired dimensional and quality performance can be confidently realized. The steps to reach robustness begins by determining the input signals and uncontrollable noise factors, as well as their respective ranges. Inputs are signals, and noise is error. Next, find as many controllable factors as possible. Select levels for each factor. Calculate the signal-to-noise ratio. There are, in fact, many ways to do this based on the type of response. We then settle on the optimal conditions and conduct production runs at these settings. Our intent will be to first focus on factors that affect average and variation, and then factors that only affect variation. Reduce the variation and then adjust the average to the target. Analyzing the amount of variation in a response helps us find the control factors that may help to reduce the variation. A signal-to-noise ratio transformation allows us to condense several repetitions within a trial into one value to describe the amount of variation present. We will discuss 3 signal-to-noise ratios based on the type of response. When we desire lowest response, we use the top signal-to-noise ratio equation. When we desire highest response, we use the bottom signal-to-noise ratio equation. Y sub I is the ith response. R is the number of repetitions. When nominal is the best response, we have 2 signal-to-noise ratios to consider. The first equation accounts for variance only, and the second equation accounts for mean and variance. Since the first equation tends toward normality for the variance and is independent of average, we could use this equation as a substitute for lower is better and higher is better signal-to-noise ratios. Recognize that these formulas use a VE and RY quantity squared for VM. V sub M and V sub E are associated with the no-way ANOVA. This is a trivial case of the ANOVA that gets little to no acknowledgement in statistical texts. We, however, need this analysis to decompose the signal with respect to noise. Let's consider this example. We have 4 trials with 6 repetitions each. We perform the necessary no-way ANOVA calculations. Note that the averages for trial 1 and trial 2 are the same, but the variation, V sub E, increases from trial 1 to trial 2 by a factor of 4. This increase in variation drops the NB1 and NB2 signal-to-noise ratios by almost the same amount, a little more than 6. Trial 3 also has the same average, but the variation has dropped below the variation for trial 1 and trial 2. The NB1 and NB2 signal-to-noise ratios have risen to their highest levels by the same amount from those in trial 1, roughly 2. Now look at trial 4. The average is higher, but the variation is the same as in trial 1. Notice that the MB1 signal-to-noise ratio is unchanged, but the MB2 signal-to-noise ratio has gone up. In summary, reducing the variation, holding average constant, increases the signal-to-noise ratios. Reducing the average, holding variance constant, decreases the MB2 signal-to-noise ratio, but holds the MB1 signal-to-noise ratio constant.